You're welcome to Physics Medicine Online Tutorial class. I remain your teacher, Mrs. Okuma Ijoma. Now today, we want to look at total internal reflection. Remember in our previous class, we talked about the real and apparent depths, where we saw the formula that connects the refractive index, the real and the apparent depth, where we have that n, which is the refractive index, is equal to real depth over apparent depth. Now we equally saw the effects of refraction, where we saw the apparent depth of swimming pool, the bent object in liquid, and formation of rainbow and what? Mirages. Now today, what do we mean by this total internal reflection? Now we have an interesting and useful effect that sometimes occurs when light travels from an optically more dense medium to an optically less dense what? Medium. When light travels from optically more dense medium to an optically less dense medium, we have an interesting phenomenon that occurs. Now, what do we mean by light traveling from optically less dense medium to an optically more dense medium? For example, when the light ray moves from glass to air. Remember in our previous class, we said that when the ray of light moves from air to glass, that is less dense to more dense medium, we said that the refracted ray will move towards the normal, whereby the angle of incidence will be greater than angle of what? Refraction. But in this case, where the ray of light moves from optically more dense medium, for example from glass, to less dense medium, which is air, you find out that on refracting, the refracted ray moves away from the normal, and in this case your angle of refraction will be greater than our angle of what? Incidence. Now we are going to study this phenomenon using a semicircular glass block. We place it on a sheet of paper, then we draw our midpoint at normal. We draw the midpoint at A, as we can see from our diagram. Then we are going to use a ray bus and direct this incident ray towards the line OA. Now you find out that on getting to the boundary, that this ray will be refracted along AB and is refracting away from the normal. Why? Because the glass is more dense than air. Now you find out that we have a reflected ray, another ray that reflected back to the glass, and that ray, we say it is weakly reflected because that ray is not as bright as the refracted ray. Now let's see from this diagram. Looking at this diagram, we have two different diagrams where the semicircular block is turned upside down and where it is turned the other way around. Now this first diagram is exactly the same with this one. Now you look at this first diagram, look at the semicircular block, and this ray now is your incident ray. So this your incident ray, you can see the incident ray in the glass. Now this ray, on getting to the boundary, it will be refracted. On getting to the boundary, the ray is refracted, and you find out that it is refracted towards the away from the normal. So you can see that. Look at normal, the straight line. Look at the incident ray. On getting to this boundary, it refracted away from the normal. Now your angle of refraction is greater than angle of what? Incidence. Now the same thing happens here from the second diagram. Let's look at it. You find out that the incident ray is also in the glass, the semicircular glass. Now you look at the incident ray. Look at it. PO. Now, on getting to this interface, PO, the incident ray is PA. Now, getting to the boundary, which we labeled PO, you find out that it refracted away from the normal. So you can see the refracted ray. Now you can see the angle of refraction, which is greater than angle of what? Incidence. Now we said that part of this ray will be weakly reflected back to the glass. And we say they are weakly reflected because they are not bright like the refracted ray. Now, further increase in the angle of incidence, something happened. Now let's look at the second diagram. Here we have increased the angle of incidence, and when this angle of incidence was increased, we find out that the refracted ray lie at the boundary or at the interface between the glass and the air, and this angle of refraction now is 90 degrees. Now the angle of incidence in the less dense medium, in the more dense medium, whereby the angle of refraction in the less dense medium is 90 degrees, that angle of incidence, we call it the critical angle. That's why we label here C. Now let's see the next diagram, which is similar to the one I just explained. The same thing. Here we have increased the angle of incidence, and further increase in this angle of incidence, we found out that the angle of refraction lies at the interface between the glass and the air, and this angle of refraction here is 90 degrees. So the same thing, the angle of incidence here, whereby the angle of refraction in the less dense medium, which is air, is 90 degrees, that angle of incidence, we call it what? Critical angle. Now we equally saw another weak reflected ray. Now finally, now further increase in angle of incidence. An interesting thing happens here. Here we have seen the increase. The angle of incidence was further increased, and when you further increase this angle of incidence, there is no more refraction. No more what? Refraction. We don't have refracted ray again, but the ray was totally internally reflected. So this ray reflected back entirely to the glass. Now look at this equivalent diagram here, where we increase the angle of incidence PA. Now in this boundary PQ, no more refraction. We label it no refraction. Rather, the incident ray was totally reflected back in the glass, and we say we have strong reflected ray. And in this situation, we say that the ray of light is totally internally what? Reflected. The ray is totally internally what? Reflected. Now let's define critical angle and total internal reflection. Remember, we have explained that using our diagram. Now, what is critical angle? We label it with C. Now we define it as the angle of incidence in the optically denser medium for which the angle of refraction in less dense medium is 90 degrees. We have seen it in the diagram. Let's take it again. Critical angle, we define it as the angle of incidence in the optically denser medium. That is, the angle of incidence is in the denser medium, which is glass, for which the angle of refraction in less dense medium, the angle of refraction is in the less dense medium, which is air, is 90 degrees. Now let's see what do we mean by this total internal reflection, which we have equally explained. Total internal reflection, we define it as the reflection of an incident ray of light at the interface between the medium of incidence and another medium of what? Lower refractive index, when the angle of incidence in the denser medium exceeds the critical angle. So remember, before we have total internal reflection, the angle of incidence has exceeded the critical what? Angle. And remember, our angle of incidence is in the more dense medium, whereby the angle of refraction is in the less dense medium. Let's define it again. We define total internal reflection as the reflection of an incident ray of light at the interface between the medium of incidence, that is the more dense medium, and another medium of lower refractive index, when the angle of incidence in the denser medium exceed what? The critical angle. Now let's see the conditions for total internal reflection to occur. We have two conditions for total internal reflection to occur. Please, this is WAEC question. They will ask you, explain total internal reflection. State two conditions for total internal reflection to occur. So take note. When you are asked to explain total internal reflection, you're going to use the diagram to do the explanation. Now, what are the conditions? Number one, light must be traveling from an optically more dense medium to an optically less dense medium. And we have seen that from our explanation, that before we have total internal reflection, the ray of light must be moving from denser medium, which is, for example, glass, to less dense medium, which we have example as what? Air. Now, the second condition, the angle of incidence in the denser medium must be greater than the critical angle. So before we have total internal reflection, our angle of incidence must exceed the critical what? Angle. Now, let's see this diagram. The relationship between the critical angle and refractive index. In this case, we are going to recall our Snell's law. Remember, we have two laws of refraction, where we said that the first law, we stated it as that the incident ray, the refracted ray, and the normal, the point of incidence, all lie on the same plane. And the second law of refraction, we said that the sine of the ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of media, and that pair of media, that is the refractive index. We have explained that in our previous class. Now look at this diagram. You have the ray of light moving from glass to air. Look at the incident ray in the glass, then the other one in the air. Now we look at this diagram. Now from this diagram, now we have our incident ray moving from the more dense medium, which is glass. Now the refracted ray lies at 90 degrees. And here we say when the refracted ray in the less dense medium is 90, that the angle of incidence in the more dense medium, we call it the critical angle. Now, when light travels from glass to less dense medium air, an angle of incidence equals the critical angle. From Snell's law, we have this equation. Remember, as Snell's law, we have that n, which is the refractive index, is equals to sine I over sine r. But in this case now, our sine r is 90. So our n, which is the refractive index of ray of light moving from G to A, which is glass to air, become sine I over what? Sine 90. Because our angle of refraction is what? 90. Now, according to our principle of reversibility of light, which we have said earlier, that the path of the light ray is reversible. From that principle, we have here that the refractive index for the ray of light moving from glass to air will be equal to 1 over the refractive index for the ray of light moving from air to glass, which is equals to 1 over n. And this 1 over n will be equals to what? Will be equals to what? 1 over sine C. Sorry, will be equals to sine C, because remember here that our angle of incidence, which is sine I, is now our critical angle, whereas our sine R is what? Sine 90 degrees, where 90 degrees is a sine 90 is equal to 1. So from here, the refractive index N of glass is given as 1.5. So from here we have that remember we said that 1 over N is equals to sine C. So sine C will be equals to 1 over, our N is the refractive index of glass, which is 1 over 5, 1 over 1.5, and that will give us 2 over 3, which gives us 0.6667. Now our C, approximately, that is sine C, is 0.6667. Then we find C. How do we find C? Inverse, sine inverse of 0.6667, and that will give us 42 degrees. So for an angle of incidence in glass greater than 42 degrees, which is our critical angle here, we will have total internal reflection. Now generally from this formula, we find out that the refractive index N is equals to 1 over sine C, or we say that sine C is equals to 1 over N, where our sine N, where our sine 90 degrees is equal to 1. Now let's take one example under this. Example: what is the critical angle for light traveling from water to air? Refractive index of water equals 4 over 3. Here we are looking for what? Critical angle. Now we use the formula N is equals to 1 over sine C, or you say sine C is equals to 1 over N. Remember we are looking for C, so we substitute. From the question we were given N, which is 4 over 3, will be equals to 1 over sine C. So sine C will be equals to 1 over 4 over 3, which when you turn it upside down, sine C becomes 3 over 4. That is, sine C will give you 3 over 4 is 0.75. Remember we are looking for C, not sine C. So what is C? C becomes the sine inverse of 0.75. And you do that with your calculator. The sine inverse of 0.75 will give you 48.36 degrees. So our critical angle in this situation, where the ray of light is moving from water to air. Remember the other one, we talk about glass to air, where we have the critical angle to be approximately 43 degrees or 42 degrees. In this case, the ray of light is moving from water to air. So here our critical angle becomes 48.36 degrees, which approximately is 48.4 degrees. Now we are going to look at mirage. Let's say it's mirage. Remember we've talked about this mirage as one of the effects of refraction. We are going to look at it in detail now. Now you find out that if you are traveling in a third road in a hot afternoon, you find out that in the vehicle, when you look beyond the road, you see something like pool of water, and you find out that when you're getting close to that point, that the pool of water disappears. That is an illusion, which we call what? Mirage. Now mirage is a natural effect due to total internal reflection. So this mirage is the natural occurrence or the natural effect of the occurrence of what? Total internal reflection that occurs at the boundary of a hot and cool air. Now, as I've said before, that we notice it as we travel along a tarmac road on a hot day, that when we seem to see simmering pool of water ahead of us, the road appears wet and shiny as if afterward rain. Now these pools of water disappear as we approach them because they are more optical illusion. They are not real. Now what happened? The phenomenon is explained by the progressive refractive bending of light from the patch of a sky or from the top of a tree as it passes through successive layers of optically less dense air. Because of solar heating, we found out that the layers of air density decreases from ground towards the sky. So as you are moving from the ground towards the sky, the density of the air does what? Increases because of solar heating. Now remember that as the refractive index of air depends on the density, so the more dense the air, the more refractive index you will have. Now the lower or hotter layer of air has lower refractive index. When the air is hotter, the refractive index will be less. Just take for instance when you have your oil, your red oil. When the red oil is thick, it will have a higher refractive index, but when that red oil has been melted as a result of heat, you find out that the refractive index becomes less. Now rays from a patch of the sky or rays from the top of a tree, we are trying to explain what brought about this mirage, this optical illusion which we call mirage. So we find out that rays from the patch of the sky or top of tree proceeding downwards, they travel from air layer of high refractive index to layer of what? Lower refractive index. So as they are moving, the ray of light is moving from the top of a tree or from the patch of a sky. They are moving from higher refractive index to lower refractive index. Now the rays, therefore, they bend gradually from the incident direction until they enter a certain layer near the ground above which the angle of incidence exceeds the critical angle. Now as this ray of light is moving from the patch of the sky or from the top of a tree, they are doing what? Gradually they are bending until at a certain point whereby the angle of incidence exceeds the critical angle. At that point you find out that the ray will be totally internally what? Reflected. So at that point total internal reflection occurs. Now the rays, they are now reflected upwards and reach the observer's eye. So when they reflect, they will reach at your eye. Now the observer sees the distant tree as well as its inverted image. Now the patch of the sky is similarly reflected and appears as a pool of water. So you are seeing that patch of sky that was reflected, and it now comes to the observer's eye as if it is a pool of water. So that is how mirage is being formed. Now let's see the applications of this total internal reflection. Where do we apply it apart from the natural phenomena which we call the mirage? We apply it in our periscope and our binoculars. Remember when we talked about reflection in our previous class, when we talked about reflection, remember one of the applications of reflection or examples, we talked about this periscope where we incline two plane mirrors at angle of 45 degrees. Now in this case, a periscope is constructed using what? Through two right angled prism. Here we make use of two right-angled what? Prism. Right-angled prism, that is the two prisms, they are inclined at 90 degrees. You are going to see the diagram. Now the light ray, they strike the inside surface of the prism at an angle that is greater than the critical angle. Remember, the critical angle we obtain in glass is approximately 42 degrees. So in this case, this incident ray, they will strike this prism at an angle that is greater than critical angle, which is around 45 degrees. Now when that occurs, the light rays, they are totally internally what? Reflected. Now let's look at the diagram. Now from the diagram, you can see the glass prism. This is the first prism inclined at 90. This is the second glass prism and equally inclined at angle of what? 90 degrees. Now you will see the objects, rays of light coming from the object, the incident ray, they will strike this prism at angle that is greater than critical angle, angle 45 degrees. When they strike this prism, they will be totally internally what? Reflected. You can see them, they will be reflected. As they reflect, look at it, the reflected ray will strike the second prism again at an angle greater than critical angle. Now they are totally internally reflected and the observer will begin to see the image. The observer sees a virtual and upright towards image. Now let's see the binocular. Let's see the binocular. Now the binoculars also make use of prisms to reduce the length of the instrument and to produce an upright towards image. So with the use of binocular also, we produce an upright towards image. We produce an upright towards image. Now in this case, the light ray, the light ray in a pair of binoculars, they are bent at 180 degrees by each prism, unlike that of a periscope. So in this case, the two prisms, they are inclined at 180, whereas in the periscope, the two prisms, they are inclined at what? 90 degrees. Another application is in the optical fiber. Now, a very important application of total internal reflection is found in the optical fibers. An optical fiber is made of a core antenna of high refractive index. A core antenna of high refractive index, such as glass or plastic. It is normally with glass of lower refractive index. Here a light ray directed into the optical fiber will be what? Totally internally reflected at the surface. Even if the optical fiber is bent, the light will still be totally internally reflected. Now let's see the diagram of this optical fiber. Now look at this optical fiber. One of the ways you can produce this optical fiber is from your coconuts. When you remove the coconut from the tree, you remove the back of that coconut, you begin to bring out those fibers. Some people are doing projects under it now. You remove the back of that coconut, the fibers. Then when you soak those fibers, we use it in producing a thick cable. We can use it in production of cables used in our telecommunication. The cables that can serve us even more than the copper cables. Now look at this optical fiber, the one that has already been produced. Now you can see the incident ray of light. It will strike it at an angle greater than critical angle. The ray will be totally internally reflected. You can see that. You can see another incident ray striking this optical fiber, the inner core of this fiber. the ray will be totally internally reflected. You can see another incident ray striking the inner core of this fiber. It is totally internally reflected. Here in this case, you can see they are bent. So our optical fiber, as I've said, I said they are now widely used in the telecommunication industries. We can carry a great amount of information than the copper wire. They can carry a great amount of information than copper wire, and they are also lighter and they are cheaper to manufacture than the copper wire. Now we look at the assignments. Number 1, describe one phenomenon of total internal reflection in nature. Number 2, derive a relationship between the critical angle and the refractive index of a substance. Finally, number 3, a ray of light passes from air through a rectangular block of glass with parallel faces 4.5 cm apart at an angle of incidence of 52 degrees. Find number 1, the lateral displacement of the ray. Then secondly, the angle of refraction, and you're given the refractive index as 1.5. We have come to the end of today's class. Thank you once again. See you in our next class.